continue to talk about this quantum oracle because we have seen it, we take it for granted. And now the first thing I want to talk about quantum oracle, the first type is called exclusive OR oracle, which we have just learned, right? So what is an oracle? It basically is a black box, right? Because in some sense, if you know what exactly is inside, then you probably don't need to do the computation, right? But the other problem is how do you create this black box? This is out of the scope of this class, right? But you just assume it works, right? It contains f of x related to the problem you want to solve. Yeah. No, constraint is just a problem. Let's say in this part is just a function, right? I want to know whether it's a constant or a balance. And no, here f of x is classical. So it's just a function, classical function. We need to think of a way to encode it. Here, when I say contain, doesn't mean that you have just this function embedded as it is. We need to do some transformation. For example, in this case, our f of x determine the basis by doing exclusive OR with y. Okay, so we don't say how you put in the oracle yet. When I say contain, I just say it has the information and probably just partial information. Yeah, good question, right? So here is completely classical. It contains the f of x, the function related to the problem you want to solve. Okay, so that is very important because just look at the Dodge algorithm. Yeah, maybe you have a very complicated algorithm, but nothing is related to the problem I want to solve. You should understand that if I want a quantum computer to solve a problem for me, it needs to know what the problem is, right? This part doesn't contain the problem. This part doesn't contain the problem. Is this quantum oracle contains the problem, right? It contains, but it doesn't mean that it will compute of f of x for you. That is very important. It doesn't compute as f of x for you, okay? But it contains some of the information. Then, of course, it's just a gate, right? Maybe very big. After all, it's just a gate, right? So it's a gate, so it must be reversible, right? It must be unitary, which means it is reversible, right? Then you think about this. If you try to construct an oracle, the most naive way to think about this, right? The most naive, or the first step, I would say, like you just asked, how do you contain f? What is f of x, right? Okay, then I say f of x is classical, and then you go ahead. Okay, let me make it quantum. Maybe how about this? I say, if we find a quantum gate U, right? This is U. Let me just call it U. I just apply to the input. Let's say it has m cubed n bit, and then it gives me the output, which is f of x. This is a way. Naturally, I will think of a way to solve. Let's say it is possible. This is a possible way to implement the function, right? You give me x, so this x can be in binary. Let's say the input is 10, then I input 1, 0, 1, 0. Okay, go to the unitary gate, and then you give me the output. The output needs to be equal to f of x, right? Because my goal is to compute f of x. But the output can be just one bit, let's say 0 or 1, right? Okay, then give me 0 or 1. This is a natural way, right? But this is not going to work. Why? What's the problem here? If I'm able to implement this, I'm able to find a gate like this, then I just put in a quantum circuit. But based on what I'm showing here, you know, it's not going to work unless m equal to n. Why? Because it's a quantum circuit, so you need to be reversible. If it's reversible, then you should be a square matrix, right? If you have m cubic comes in, then I have m coming out, because in that case, then I can reverse it. It means I can have the m cubic in and then m cubic out on the other side, right? So then I would say, for example, I should also say example, right? You may say x, okay, I just pick x from the binary number, but it has m qubit. Y from the binary number, right? It has n qubit, right? But this is very important, n equal to m to be reversible. Because after all, U is a matrix. Right? If it's reversible, you need to be a square matrix. Right? So that is the first thing that we already have quite some progress. We understand, yeah, this is a good way, but I definitely see, no matter how smart I am, I cannot come up with a U that take m bit qubits and give me n qubits if m not equal to n. I need to work in the same Hilbert space. Right? So then many people are very smart. Then they come up with one idea. How about this? I have one possibility is that I can encode the f of x into the basis. But here, I don't just put it as f of x. I'm putting exclusive or f of x. And because of some reason, we are going to show it later. There are different types of quantum oracle. This is one of them, right? A common one. So I encode the f of x into the basis. So look at this. On the top is MSB at the bottom. So you see that I have n qubits of MSB coming in, m qubit or LSB, right, on the top, and they are x and y. And then what we are going to do is that after this oracle, the oracle need to function in this way. I should say the oracle need to function in this way. Then we call it exclusive or oracle. That this n qubit doesn't change. The x doesn't change, right? But the y become y exclusive or x. Then you can imagine, let's say if my f of x, the output, like the balance and constant case, I only need one qubit, 0 or 1, to indicate whether it's balanced or constant, right? I just need to make m equal to 1 so that I can do this exclusive OR. I don't know if you follow me, right? But the main point is here first. Quantum oracle is a black box. We need to find a way to encode the function that we are interested in it, because we do need to solve the problem. You need some quantum gates to contain the problem to solve it. Is this okay? Right? That is one thing. Second thing, how do you construct it is very difficult. We are only looking at toy example to construct it, but in general, to do a useful problem, how do you do it? We were not discussing here, because I'm not good enough to discuss this. But we take it for granted. We trust the mathematician to come up with an effective way for us to construct the quantum oracle. Is okay? The second thing, right? And then third thing is that now we need to make sure it is a square matrix, it's reversible. So we need to make sure that the number of input qubit is equal to the number of output qubit. And one way to do this is to have this function, which we don't know how to implement this directly here, but we know that this is the requirement, right? So basically what I have been saying is just repeat what we learned earlier. U, F, apply to x, y needs to give me x, y exclusive or f of x. Is that okay? So now I'm going to prove that to show that it is reversible. Yes, I try to ignore it, correct. X has subscript n, and, no, X has subscript n, yeah, n instead of m, right, n, and Y have m, n, m, right? So in the Deutsch problem, it's very simple, n equal to m equal to 1. Okay, because we're like one input, one B input, right? And then one QB output. So I want to show it's reversible. This is very easy. So what do I do? So I apply UF to X and YM. I do it 2 times. Okay? So let me look at the first one. When I apply the right one, this one, right? UF into here, what do you get? By definition, by the requirement of by the definition of the exclusive or oracle, what do you get? Huh? You already have the answer on top. What's that? Xn y exclusive of f of x m. Thank you. Are you okay? Yeah. Anyone has question? Anyone cannot see this? From here to here, I just have an extra UF. The rest is just the definition. Huh? Make sense? Now I want to apply one more time. What do I get? Again, by definition, it really doesn't matter. Now this whole thing is y. This whole thing is x. So x is still x, right? And then how about the y? This whole thing is the y going into the second UF. This is the original y, right? It need to be exclusive or with f of x. Make sense? Right? So again, what does this unitary matrix does? It takes x and y and it keep x as it is. But for y become y exclusive or f of x. This m should be outside. Right? This is the function of the exclusive or quantum oracle, right? You keep x and then y becomes y exclusive or f of x. But now I apply one more time, right? Because I have 2 UF. When I apply the second one, again, this is x, this is y. So you keep x, and then this whole y will be exclusive with f of x one more time. Make sense? Then what is this? Well, fx, this is, what do you call, associative, right? F of x exclusive or f of x give you what? Yourself exclusive with yourself, 0 exclusive with 0, 1 exclusive with 1. What's that? 0. So this is always 0. So this one will give us x and y exclusive or 0, which is x and y m. Correct? So basically this say that if you apply this one, you apply 2 UF to XY, you get XY, no matter what XY. So UF apply 2 times, give you the same thing. So UF must be equals to which matrix? Identity, very good, right? apply it 2 times, it gives me the same thing. Then UF must be identity, right? By definition. But we also know that for any matrix, UF times its inverse must be equal to 0. Right? That's the definition. Matrix times equal to 1, equals to identity. By definition, any matrix A times A inverse must be equal to I. Unless you don't have the inverse, not every matrix has inverse, right? But I show you that I do have UF times UF equal to I. Then it means this UF is its own inverse, right? So there exists F inverse equal to UF, right? And exists, and it exists, right? And based on this, it is reversible. If you have a inverse, then it means you are reversible. Okay, so here just to prove, but then why I can prove that this is reversible? Why we construct in this way, make it reversible? It's just some smart way you see that Y exclusive with UF, F of X, give this property because we're using exclusive OR. Some of you came up with something different. Let's say, how about NOT gate, right? Do the not, and do the and operation between Y and F of X. In this case, you will get Y and F of X and F of X. Then this one is not going to be identity. This is not going to be reversible as trivial as this one. Right? So the way we construct it, right, it is reversible. So it's just reversible by construction. So exclusive or quantum oracle is reversible in this sense, right? So there's a reason behind it why we construct the quantum oracle in this way. But I do want to draw your attention that when I do F of X exclusive with Y, do you think that we lose some information of F of X now? Or the quantum oracle has all information about F of X? What do you think? Yeah. You lose information. I mean, not just output, you just lose the information about. Okay, and the output I know. So from looking from outside, right? But yeah. When I say I lose information is in this way. If I want to know F of X, there should be a way, no matter what X I put in, you should give me the corresponding F of X, right? Then you say, I have all the information. But now you try to do an exclusive OR with Y. Then it means you actually mask it by something, right? For example, maybe one F of 0 and F of 5 are different, but after exclusive with Y, they might be the same. Yeah. So I lose some information, right? So again, this goes back to the original for, again, you use quantum computing, you can do parallel processing at the same time, but you actually don't get all the information at the same time. So by sacrificing some of the information, we actually can get another piece of information faster. That's what I want to say. Yeah.
Do we lose it before the measure? If it's reversible, we would have had to have some way of getting the information back.
When I say I lose it, I mean by construction, because UF, you give it X and Y. it gives you y exclusive of f of x, right? And that is what I mean by loose, not inside, because go back to your hesitation at that time, you say look from outside, right? But this one is just that what I'm trying to say, we actually don't embed f of x in the machine, in the gate, right? We use f of x to create some gates, but when we create it, it only mandates that the output is y exclusive of f of x. It does not mandate the output to be f of x. Right, so this machine is there. How do you extract f of x in this case? You never can extract, you don't extract f of x, right? You only extract y exclusive f of x. And that's what I mean that you lose some information about f of x.
Okay.
Yeah. So I did not say it well. So how do you extract f? That is, let's say you really can do it classically. Just look at this. Do classical simulation. You cannot get f of x anymore. Or let's go back to this simple example. This one I have all information of this whole machine, basically. But by just looking at this II, you cannot tell me, you really cannot tell me what function it is. Because it can, whether this is, maybe you can actually. Maybe this is not a good example, sorry. But anyway, I always say that we do lose some information. Okay. Okay, so there's one type of oracle, and then now I take this opportunity to introduce another type of oracle, because this type of this oracle will be used in our next algorithm. So this is called phase oracle. So what does it do? Okay, so look at this function. The input is NQ bit and is x. After this oracle, it is still x. However, it has a phase. Its prefactor become -1 to the power f of x. Again, we embed f of x in this oracle. It has some information about the problem we want to solve. But again, we lose some information, right? Because I can only get -1 to the power f of x. If your f of x is even, it always gives me 1. If your f of x is odd, it always gives me -1. So I cannot distinguish whether it's 1, 2, 3, 5 or 2, 4, 6. So let's take a look slowly, right? So if f of x is even, then -1 to the f of x is 1, right? And if f of x is odd, then -1 to the power f of x is -1. Right? You should know that. And I'm writing too big then. So in this case, let me continue, right? Then UF of x will give me what? Will give me x itself. And when it is odd, UF of x will give me -x. So do you see that this quantum oracle is very simple? Basically, it's just that you give me a basis, and depends on the basis number, it will be yourself or just negative of yourself. And when I say negative, I mean the phase is -1 in front of it. Is this clear? Any questions? Sense? Maybe so simple that you wonder why this can be an important thing in quantum computer was supposed to be something very mysterious. Now I can pronounce it. Right? But it is so simple. Okay, so that is the quantum oracle, right? So my goal is to again show that why this is a good oracle, right? Or why this is a good quantum gate. Because I'm going to show reversibility, which is very easy. So again, I use the same method. I apply UF 2 times to x. So in the first time, what do I get? -1 to the power f of x times xn. right? That is the definition of this phase oracle. Is that okay? Now, if I apply UF one more time, what do I get? By definition. Thank you. Maybe very simple, right? But this whole thing is the new input. What you're saying is that whatever new input you give me, I multiply by -1 to the power f of x. So this is -1 f of x, -1 f of x, xn, right? But to -1 f of x, no matter whether you are even or odd, it will be 1. Very good. So this becomes xn, right? So based on this, again, we have the same situation. You apply it 2 times, you doesn't change the vector at all. Then it means UF equals to identity, right? And then since we know that UF minus 1 equal to I, then it means UF minus 1, which is the inverse of UF, exists. And we also know, not just know that it exists, we also know that it equals to UF itself, right? So therefore UF is reversible. Just want to take this opportunity to mention that this is just a special case of phase oracle. There are some more general phase oracle we will not discuss in this class, but I just want to let you know so that in the future, when you study or see paper, you will not be surprising. This should be f of x. The general oracle is e to the power I. Is that right? F of x. Okay, but we won't go into details. So we'll only discuss this in this class, okay? Are you okay? Any questions about phase oracle? You need time to memorize it, but it's the same as the exclusive OR. They are reversible, and they are very simple. You just follow the definition, and that's it. Okay? So then, today I want to talk about the Groover's theorem. Before